In recent decades, neural networks have become a popular tool for modeling artificial intelligence, and an important task is to mimic creativity by synthesizing new content. Variational autoencoders are neural network architectures that can be used for this type of task. We can use the embedded toolchain to model and train this architecture effortlessly and deploy them in applications. This video can be split into two parts. First, I will explain what variational autoencoders are to give you a basic understanding of how they work. If you are already familiar with this model, you can skip this part and jump straight to the main part of this video, in which I will show you a few examples of how you can use the toolchain to model variational autoencoders. Now, let's have a look at what autoencoders are. Here we have an example in which images are processed. Images can be expressed as matrices, whose entries contain the pixel values. This data is given as input to a neural network, which is called encoder. The encoder compresses the input matrix into a lower dimension, resulting in a numerical code that represents the content. The decoder, another neural network, can use this numerical code to reproduce the original content. In order to reconstruct the image, the code expresses properties of the object, for example the color, the shape, or similar features that can describe the content. A variational autoencoder, or in short VAE, can be split into a training and runtime stage. In the training stage, the networks are trained to reconstruct images of a training dataset, while the runtime stage is about using the trained decoder to process arbitrary codes to create new images. The main difference between VAEs and autoencoders is the process of how they map their codes into the latent space. The codes of autoencoders are mapped rather arbitrarily into the latent space, making it difficult to choose a code that leads to the creation of meaningful content. It is more likely that the chosen codes would result in contentless pictures. The encoder of the VAEs do not compute this code directly, but parameters of a probability function, such as a normal distribution. The code is then sampled from this distribution and processed by the decoder. This ensures that the codes are squeezed into a certain space, so that codes that represent similar properties are mapped into the proximity of each other. After training this model, we can sample from the probability distribution, which gives us a code that has a high probability of representing content. The code can then be processed with the decoder to generate the new unseen data. Apart from the standard VAEs, there are also variants that can be modeled using the embedded toolchain. These variants include the conditional VAEs, which give the user the ability to choose the content to be generated, and beta VAEs, which disentangle the features expressed in the codes. This variant can be used to arrange the latent code space more properly, so that a user can work with the codes in a more convenient way regarding the generation of the content. There are also DVQ-VAEs that learn discrete representations rather than continuous ones. This model can only be partially modeled in Embedded yet, as it is still in development. You can still use the toolchain to save some effort when you need to work with them. Now, let's look at a couple of examples of VAE models in Embedded. We create a directory in which we place our Embedded files. To model VAEs, we need two neural network components. Here you can see the encoder component, which is used to calculate the codes of the input data. The dimensionality reduction can be seen via in the part definitions, which are needed to link these with other components. This reduction is done by the processing of a neural network, whose architecture can be modeled by placing layers within the implementation CNN body. At the end of the network, we use the reparameterized layer. This element is responsible for the sampling process of the code from the normal distribution, which is calculated from two data flows representing the learned mean and standard deviation. Next, we need a neural network representing the decoder. We use this component to restore the original dimension of the data that entered the encoder. The last embedded file is used for the description of the system that will be used in the runtime environment. Here we instantiate the decoder component that will be used as a generator after training, and connect it to the parts that are defined in this component, which will be used as an interface to transfer data between the neural network and the application. Furthermore, we need a configuration file in which training parameters are set. The most important parameters are the first two that are listed here. The learning method must be set to VAE so that the modeled components can be validated for their completeness and correctness. A reference to the encoded component is also required, since the component is not instantiated and therefore not recognized otherwise. For the remaining parameters, default values would be used if none were assigned to them. What the other parameters are used for can be looked up in the Git repository of the VAE project. Finally, we create a tag file that we use to set a reference to the dataset with which we train our VAE model. Here we use the MNIST dataset featuring images of handwritten digits. If the files have been created, we can use the code generator with the Maiden plugin, or a local version of the generator, shown here, to generate the executable code and to start the training of the model. Let's look at the new files. For the training of the models, the Python code shown here were used. C++ code was also generated that can be used to embed the modeled system into an application. We only need to initialize the generated class that will be used as the interface, assign the variables that were modeled as input parts, and then execute the system. The output can then be read from the output part variables and be further processed in the embedded application. After the code generation and training process, all the necessary components have been created, so that we can compile our C++ application. In this simple application shown on the right-hand side, we manually provide the values of the code and process them with the VAE model, which in return yields us an image. This example shows a model of a conditional variational autoencoder that is used to generate particular content, which cannot be done with the standard VAEs. We can use the files from the previous model as a template and add the features that are required to model this variant. The feature we need to add is an additional port in the encoder and decoder components. This port contains the labels that classify the corresponding data that are processed with the neural network. We also modify the network architectures in order to concatenate the labels with the data. The rest corresponds to the standard VAE. Don't forget to adjust also the main component to the model accordingly. Since we trained the model with the MNIST dataset, we can control which digit our image should display. We use the same simple application as before, with the difference that we don't provide the codes directly, but seeds for a random generator that samples the code from the normal distribution. We simply enter a seed and a digit and get in return an image with the expected content. There is no real difference between the beta VAEs and standard VAEs. You only have to configure the KL loss rate parameter. A value greater than 1 would disentangle the properties in the codes. A value smaller than 1 puts the focus on the reconstruction quality. The VQ VAEs are modeled by using the vector quantized layer instead of the reparameterized layer. This layer trains a codebook containing vectors that are needed for the discrete codes. These codes are feature maps computed by a convolutional neural network. Except for the vector quantized layer and the feature maps as codes, the modeling is conducted as for the standard VAE. In order to generate new images, certain feature maps have to be composed using the vectors of the codebook. This composition is done with a PixelCnn, a neural network that is not yet modelable in Emmade. Therefore, the network has to be implemented and trained by the user. The PixelCnn generates feature maps. Those pixels of each position across all feature maps are replaced by the entries of the vector closest to the pixels in terms of values. The new quantized feature maps can then be fed to the decoder modeled in Emmade that generates new images.